Thank you very much. It's a little frightening to hear that you've been working in industrial inkjet printing for 30 years, but there you go, it's true. Can't do anything about that. I'd like to thank the organisers for giving me the opportunity to speak today, and it's really very nice to see so many people interested in inkjet technology, and it sort of smacks of the buoyancy that seems to be around. Alchemie Technology is another industrial inkjet company based in Cambridge in the UK, but that's about where the similarity ends. And the technology, the inkjet technology that we're developing, is about as far away from traditional inkjet technology as you can possibly be and still define it as inkjet technology. And we're really focused on being able to apply all sorts of materials, including exotic materials, for digitally applying these to a whole range of applications. And that's really what I'd like to talk about. So for those that don't know Alchemie, we're 2 years young, although the team goes back longer than we care to think. So we're all about developing a range of digital technologies, liquid inkjet, and also capable of digitally applying powders and metals directly. And there's some of the things that I'd like to talk about. And we're developing our own technology under this name called Jetronica, and it's all about selectively patterning high volume liquids or powders. So very much different scale to traditional piezo drop-on-demand inkjet. And we've reached a stage now where we're supplying modules for integration by OEMs, and pretty much all of the technologies I mentioned are patented. We also, because we think there is a need, we also have a relationship with Trident. Trident is a USA printhead company, whereby we put together Trident printheads to create highly precise industrial production line applications for deposition. And we can supply anything from a printhead all the way through to an integrated solution, ink or the modules for that. And then the other thing we do, because like Holly, education is important. And although her ambition was quite impressive in terms of wanting to help people, I would be just happy if one person's still listening at the end of this presentation rather than anything else. But we also offer a contract development service to develop new inks for high performance applications, and we also can develop industrial inkjet systems. So contract development based on commercially available printheads, and we do this to really stay state of the art and to keep up with what's happening with inkjet. And we've helped a number of customers almost on a consultancy basis to do that. So I'd like to first talk about this suite of technologies that we have called Jetronica, and it's all about digital deposition of liquids and powders. And probably like to talk about the liquid technology first, and then highlight some of the powders. And the industrial applications that we're focused on is really all about selectively patterning protective coatings, applying coatings on production lines, dispensing adhesives, putting inline pre-treatment inkjet systems for textiles and labels and all sorts of applications. We're also interested in applying functional coatings, so 3D applications where we're directly applying metal powders such as titanium and tantalum. Biodispensing of medical devices, so we're doing a lot of work dispensing drugs to create either a very customized, specific dosage for a patient of a 3D printed pill, or an implantable drug that gets put into the body to release the drug over a well-defined period of time. And we're also now routinely with Manchester University, so much of this functional coating and material science application is being carried out with Manchester University. We're also now routinely printing graphene and maintaining the properties of graphene. And those that are aware of the last 10 years of development of graphene, what's really difficult is to be able to process graphene to produce the properties of graphene without it reverting back into graphite. And we've developed some ways, and our technology is now capable of printing graphene and maintaining the properties of graphene. So this is quite a disruptive approach to many things. So our technology has all the benefits of digital, and that's really what we set out to do, to find a digital technology with all of those great benefits that everybody's interested in, but also have this flexibility to be able to use a whole range of materials that are more associated with analog fluids, analog materials, and analog printing. And so this digital technology, we can now tune coating weight, we can create layers, control layer thicknesses, and above all, we think this is a proposition that suits industrial applications and industrial production lines because it's a low-cost, high-throughput proposition for many industrial applications. If we look at it, then here is the jetting assembly. So it's very simple. It's highly productive. Has very high productivity. It's a very low-cost design, but it's capable of very high throughput and high volumes. And I'll try and describe that a bit more. So it's very robust. It's all stainless steel with the piezo crystal, refurbishable, very fast returns on investment, extremely high liquid flow, and a drop volume range from nanoliters up to microliters, as opposed to being constrained to picoliters with traditional inkjet. So it's really, the difference in this is really all about being able to jet higher viscosity fluids, 200, 500 centipoise, so 20 or 50 times greater than traditional inkjet, and volumes rather than in the picoliter range, in the nanoliter and up to a microliter range. And that gives you tremendous flexibility in terms of production line applications. So this jetting assembly is based on a piezo needle construction. It's simply a stainless steel capillary tube that has a tip that looks like a hypodermic needle, and a piezo crystal is micro welded to this tube, and the dimensions and the angles and everything associated with the configuration is important to be able to generate a standing wave when the piezo is activated, which travels through the fluid, and at the tip, the arrangement at the tip is such that we get this massive amplification, and as the meniscus is disturbed, this tip vibrates. So it's different again from traditional piezo drop on demand, in the sense that this tip, this nozzle, actually vibrates and is displaced about 10 microns. So as we excite the tip, it moves up. It disturbs the meniscus, liquid flows onto the outer surface of this tip, and on the downward movement, it flicks droplets onto the substrate. And it can flick droplets over large throw distances, because the volume of these droplets are so high in comparison with traditional piezo. Traditional piezo is all about trying to throw feathers through this high resistance of air. These are more like cannonballs being ejected from this tip, and so we're able to jet them over centimeters, many centimeters, as opposed to millimeters in terms of throw distance, without losing any properties. So we can do this at quite high speed, up to 2 meters a second, and we can vary the drop volume and we can then stack these jetting assemblies to create a traditional print head that's suitable for a lot of industrial applications. So the downside is the ability to stack these and get a decent resolution. However, because the volumes are so high, there's no point in putting them too close together, because we can generate very uniform coatings and very, very high thick coatings at a fairly low resolution. So this is the ejection process. So we get this spray of droplets from the tip, not from the meniscus, and you get this conical arrangement coming out. And that has been the challenge to develop and optimize so that we can control that process very effectively. And just to complete the operation, we get this, we apply the standing wave, and then because of the tip, we get this massive displacement at the tip, and also a massive reduction in the vibrating mass, and that gives this ability to overcome the threshold of firing these droplets from the tip of the nozzle. And we can vary the number of droplets by simply changing the excitation time. So the longer the excitation time, the more droplets we can produce in one cycle to get these effects. So one thing to point out, this technology is not suitable for graphic applications. It's really suitable for selectively patterning rather than high-resolution graphics. So if you're interested in high-resolution graphics, this is not a solution for it. So we can jet a wide range of fluids, similar to analog fluids, mentioned up to about 500 centipoise, a whole range of different materials. Particle size suddenly doesn't become that big a problem, and so pigment dispersions with 10, 20, and even up to 50 micron particles in a dispersion can be jetted using this technology. And we can use a wide range of viscosities and control volume. And because it's all stainless steel, it's inert to a whole range of chemistries. So we're focused on adhesives, industrial product coatings, textile pre-treatments, textile coating, textile dyeing, a lot of biofluid deposition, and then there's a whole range of additive manufacturing applications and selective powder coating applications. And we supply a range of modules from jetting arrays, where we've developed our own onboard electronics. It's taken time, our own ink systems, and all of this is relatively more straightforward and simpler than inkjet. So inkjet is highly sensitive. You have to worry about a huge amount about the details. This is a lot simpler than inkjet. And we've also built our own application-specific motion handling system so that people can take these things and develop solutions very quickly. And we have print heads ranging from 4 inches up to 20 inches, and then you stack them for big. So if you just take a fluid without doing anything to it, then typically you get this type of performance on the left, and you can see there's a lot of atomization, but it works, and that's pretty much any fluid will work. And then you go to the and you change a few printing configurations, drive voltage, and other things, still without changing any chemistry, and you can start to control this atomization and control the performance much more effectively. And then if you want to optimize it a bit more, then you can start to tune the viscosity and the surface tension to the drive voltage and things like that. So a relatively simple process. So as an inkjet person, it's quite difficult to come and use the word simple in any development process, but we're hoping that this will be a simple development process for a lot of different applications. And we've put some evaluation systems together, and this is just a selection of simple depositing, one nozzle depositing to 4-inch bars, and even 20-inch bars together, so that these can be evaluated very quickly. So that's liquid inkjet, Jetronica technology. I'd like to just describe some things, and this is the first time we've we've sort of gone public on this. So I'd like to describe some of our activities that we've been pursuing on Powderjet, dispensing powders using a digital process. And we have a number of different techniques, and I'm not going to describe all of these techniques, but you choose a technique depending on what sort of properties you want. If you're interested in vertical height, then we have a technique for that. If you're interested in very strong covalent bonding to get powders that stick together very firmly before they're fused, then we have a technology for that. If you want very high resolution, an inkjet resolution, we also have a powder technology that's capable of delivering very high resolution digital powder prints, except the particle size is clearly going to determine how high resolution you can achieve. So in all of these powder jet technologies, we're not really restricted by particle size. And we can go from micron up to several hundred micron particles. And the whole point is to take the complexity of the chemistry away. Here is just a very simple, very crude video of a nozzle that's several centimeters away dispensing glitter. And this glitter is an irregular, just showing it's a very irregular shaped 400 micron particle size just being sprayed onto a surface from a single nozzle. And then if we look at typical commercially, so on the left we just got commercial grade titanium dioxide just digitally being applied. It clearly requires a fusing or a fixing technique after, but to show you it's a powder. And titanium dioxide, that's just powder being digitally dispensed. If this right-hand video hurries up a little bit, which it won't, of course, it can show not only can it, if you reduce the height of the nozzle from several centimeters to about a centimeter, then the resolution or the fine line of this very difficult glitter type material creates a much finer line. So you get the message of this sort of conical effect that's generated. So the nozzle there is about 500 microns to give you about a scale of how wide these lines are. And then if we move to 100 micron titanium powders. So this is just pure titanium powder being jetted using this technique. Again, that nozzle is about 500 microns, and you can see the amount of material that is being deposited, and you can see the sort of 3D profile that's being generated using this technique. And again, this is just regular, commercially available, off-the-shelf titanium metal powder, and we've repeated it using tantalum and other metals as well. That's a technology, digitally applying powder. We also have another way of digitally applying powder using ultrasonics. And what this does is you apply a very loose layer of powder onto a surface without any digital, just a simple layer of powder onto a surface. And it's all very loosely held, and that's critical. And then we come along with an inkjet print head, a very high-resolution inkjet print head, and it can even just fire water. It doesn't have to have any fixing agents or anything else, and this water goes directly through this loose structure and actually causes it to bond causes these particles to agglomerate and bond onto the surface very effectively to produce a very high resolution image. And then after we remove the powder, and then we can fix it or to get permanent durability if that's required. So this is an illustration of what I just said. Ultrasonic dispensing of a powder, creating a loose structure. The high-resolution inkjet print head fires a drop through this powder to fix it onto the substrate. You blow the powder that's not been fixed away, and you have a very high-resolution image using particles that would be very difficult to inkjet any other way. Here is another technique, powder technique that we're using as the basis to print pills, customizing it to be very patient specific. This is an inert material, but it gives you the impression of the type of effect that we can generate. And with using that technique, printing simply onto a ceramic tile in this case, you can see that we've put layer upon layer and expanding it. You can see the type of vertical heights and the vertical layers that we can produce. None of this has been fused. This is just printing a layer and a layer upon a layer to build this structure in height. If you turn this upside down, it would just stay as it is. If you hit it with a hammer, it would break. You would have to fuse it to get that sort of mechanical strength. But as far as building complex 3D structures, then there is enough robustness and strength in these vertical layers to be able to do that. And of course, you get rid of all of these problems of 3D printing, of having stress in between the layers that you're printing, if you're able to print the whole three-dimensional structure in this way. So building layers in height is something that we're interested in doing. So some of the benefits of also considering digitally printing powders as well as liquids is very much we have the ability to selectively pattern. We can do this in a very low cost, high resolution with a digital printing capability. We totally remove all of the problems and complexities of the chemistry from this digital print process that is hindered and prevented progress over many years. And we've reached a stage where we can pretty much jet any powder using one of three of these techniques, and it really just addresses this problem of larger particle size no longer becomes an issue in terms of being able to jet the material. So we're no longer compromising the performance of these properties, and generally we see that you can use off-the-shelf materials to do this. And these are some print samples of liquid and powder samples being jetted. It's just some typical samples. It's not focused at graphical images, as I mentioned, but I can't persuade anybody not to produce a graphical image to demonstrate the capability. So where are we going with some of these things? Well, we're very much going down the route of creating customized peel printing. We're very much going down the route of creating implantable drugs. The whole medical industry is looking for taking the control of the patient out of the treatment. And so if you can imagine an onion structure and in between on a millimeter scale, and in between each of those layers of the onion, you're able to put a dosage of a drug, then you can implant this device. And if you've customized it to the pH of the stomach and the pKa rate of the patient, then you're able to very accurately be able to dose the amount of drug over a long period of time, say a month or 6 weeks. So there's a lot of interest for very nasty, difficult diseases like pancreatic cancer and bowel cancer to try and develop techniques and things like this to do it. Specialty materials, we certainly see there's a huge future now in being able to print graphene for a whole range of applications. The thinnest material in the world, a third of a nanometer. The stiffest material in the world. The most highly conductive material in the world. A very high conductive of heat. And many other, and with 97% transparency if it's contained as graphene and not graphite. Titanium and other metals to produce very lightweight, high-strength components for a lot of 3D printing applications. So that's the technologies that we're developing. We also offer Jetronica, which is the Trident-based solutions, and I just want to make people aware of it because these provide instant solutions for a lot of applications. So we have this partnership with Trident, and it means that we're focused on supplying Trident print heads and becoming their integration partner for industrial applications. So any application outside their core market, which is coding and marking. And over the last year, we've been developing, we've created developers kits. The products that Trident had for these sort of applications were a bit suspect in the past. So we've put a lot of effort in creating our own electronics, our own software, our own motion system, so that customers can select one or many of these different modular components to evaluate for an application. We've just finished that exercise, and we're basically trying to make it as simple as possible. A 256 jet Trident print head for higher viscosity fluids, a low viscosity version, and a universal version for high and lower viscosity. And of course, with Trident's a fantastic industrial print head for evaluating an industrial application, because you can take the thing apart and put it back together many hundreds of times. So you don't need to worry about blocked nozzles so much, and we can change nozzle diameter so that you can tune your drop volume to the chemistry in an appropriate way. And now I'm pleased to say that we have our own dedicated electronics and software to support it. And just to put things in perspective, this is the way in which we see things and how we differentiate from traditional graphics inkjet print heads. So the traditional piezo drop-on-demand inkjet graphics heads are highly sophisticated, fantastic print heads for what they do, and they're really been focused for many years on picoliters and these sort of speeds, and it's a domain that they dominate in, and we have no interest in going there. And so Trijetica is a bridge between our Jetronica technologies that we're developing, and our Jetronica technologies enable us to go to much higher speeds and much higher drop volumes, and that's the relative difference in these propositions. Excuse me. And similarly, if you plotted resolution versus cost of ownership, then resolution doesn't come cheap. These graphics heads have tremendous resolution, dots per inch, but that costs a lot of money. We're at much lower resolutions, but remember, much higher drop volumes, and the cost of ownership is significantly different, many times different. And the same goes for the Trident-based printhead. The cost of ownership of a Trident-based printhead over its lifetime is one of the lowest cost of ownership inkjet printheads there is on the market. And finally, when you look at coating thickness and you look at viscosity, then this is the area that we're trying to dominate, being able to supply deliver fluids with a variable coating thickness way up into over 50 microns, and viscosities way up from 200 to 500 centipoise. And this is how we compare with the traditional piezo drop-on-demand printheads. So we're trying to push inkjet really into new applications that, quite frankly, is impossible to consider with traditional inkjet technologies. And that was our premise when we started looking for this technology and ended up with Jetronica. We wanted to find a relatively simple digital technology that was capable of competing directly with screen, flexo, powder, and spray coating applications, because we see there's a huge amount of interest for a lot of applications in this area. And what we're trying to do, what our aim is, to remove all of these limitations, and that is speed, layer thickness, particle size, the complexities associated with the chemistry, making things simpler and therefore more reliable, but above all, make the cost proposition more akin to an industrial process, rather than a very high technology proposition in an industrial environment. So finally, just leaving you with some thoughts of. There's no doubt that inkjet is trending away from its graphics heritage. It's done fantastic. It is doing fantastically well, printing graphics and images and graphical images. But there is definitely a trend towards truly industrial solutions for additive manufacturing. And this is evident by Czar, Kyocera, and even more recently TTEC announcing that they're supplying print heads with larger drop volume. But we think we're many factors higher in terms of drop volume for a lot of these industrial applications. And I think the confidence for inkjet and taking various inkjet technologies into industrial applications has really been boosted by the success inkjet has enjoyed in printing ceramic tiles, and the success is beginning to enjoy in terms of printing onto textiles. So everything timing is good as far as exploiting many of these industrial applications. And we certainly, not alone and with others, we're trying to push digital printing into many of these highly core industrial applications. So thank you very much. I think that's all. Yeah, it is. Thank you.
Thank you very much. Are there any questions? A couple of questions, just in the order.
So long as they're not difficult.
As for coatings, you said you can bring up to 50 microns coating thickness, but what about the surface? Can you cover the complete surface? So could you make a film, for example, on the surface?
I would be highly confident that we can make a film and the topography would be uniform rather than undulating as a result of, well, I guess if you print UV cure ink using a traditional inkjet head, then you tend to get an undulating surface. I say that because we're not printing a drop, we're printing a collection of drops of different sizes, and they're much bigger volume. And no matter how high a surface tension you have, when you get to a certain volume and a collection of drops, these all surface tension dominates, and surface tension will pull it into a film. So I would be very confident, even at quite a low resolution, to be able to produce very uniform films.
I had a question about coatings as well. So
right.
How far along are you? I mean, is it still in the lab and pilot scale? Are people actually using it for manufacturing purposes?
Right, somewhere in between those 2 points that you made. So we're definitely beyond the lab. We have early adopters, so we have customers who are in the process of introducing them into their factories, or their production lines to use it. There is a commercial product out there that is using this technology. So it's at the early stage of commercialization, but there are a number of customers who have gone past the lab stage and are now looking to see how they scale it into a production environment.
Other questions?
Thank you. This technology can substitute a roller machine.
Can substitute
a roller machine.
A roller machine.
Yes.
What?
A roller. Imagine a roller that applies a white paint, or some primers and coating.
Yes, but it's got the advantage of being able to selectively pattern, whereas I guess a roller doesn't, unless you have a relief pattern. But you can change the pattern on demand, of course, with a digital process.
Okay. Thank you.
Yeah, it's just the powder dispensers. So if the particle size is very small, is the nozzle easily blocked or is okay?
So the finer the particle size, that's a good question, and I'm trying to answer it without spending 10 minutes answering it. To get the particles to flow, you have to tune the Powderjet technology to the particle size. And there is a tipping point where powder starts to behave like a fluid. And generally that's how we tune the system to the particle size. So it can use a wide range of particles, but generally you have to configure the machine for a particular particle size. We've jetted, I don't know how fine you mean, but we've jetted without any difficulty sort of 1 micron particles. We've some starches and some sugars for drug encapsulation. We've managed to jet without a problem. So, but I don't have enough experience or data to be able to answer that question, other than we've got a little bit of experience to suggest it's okay. So you probably know more than me.
You mentioned ceramics, and I confirm there is a strong interest in this field for a dry application.
For
a dry application of powders.
Powders onto ceramic?
Yes.
Yeah.
In the past, we saw an attempt to introduce a Jetronica-like technology with a vibrating tip. Have you any experience on ceramic decoration?
Yeah, we've we thought that was one of the going to be the first applications, and we've tended to shy away from it because of the saturation of inkjet in the ceramics market. But the idea of when the biscuit is produced, then throwing powder onto it, we've taken some of those commercially available pigments and put it through the system, and it's jetted finely. I think the experience that you're talking about in the past didn't align the particle size with the configuration of the vibration.
Probably not.
And that's key to getting these particles to flow.
We'll speak more in detail.
Okay.
Any other questions?
During your lecture, you mentioned the maximum viscosity would be something like 500 centipoise, or is it really the maximum? Or
no, it's not really the maximum.
Yeah.
And it depends on the chemistry and the type of material and the rheology. We have experience of jetting fluids at 500 centipoise. We don't know where the limit is. We have had some big difficulties at 1,000 centipoise, but we've sufficient feel to indicate that given time we could probably push that 500 centipoise up to maybe approaching 1,000.
Do you have any experience with jetting, let me say, the preparation for reactive dyes, what you normally use, or what you normally do by padding?
Pre-treatments?
Yes.
Yes. Yeah. Yeah, those viscosities we've been able to jet chemistries for pre-treatment. Yes.
Okay, thank you.